Welcome back. In the last section we talked about validation and we saw some drawbacks with that method. Now we're going to talk about k-fold cross-validation, which will solve some of these problems. This is actually a very important technique that we're going to use throughout the course in various sections, and also something that we use in our work all the time. So it's really important to understand k-fold cross-validation. It's used for a lot of methods. It's extremely flexible and a powerful technique for estimating prediction error and to get an idea of model complexity. So what's the idea of k-fold cross-validation? Well, it's really in the name. It's validation, as we've seen, but done sort of like a k-part play. It's done k times with each part getting to play the role of the validation set, and the other k-1 parts playing the role of the training set, which I say here. But let me go to the picture here, and I'll sort of point the picture as I say it. So here we're doing 5-fold cross-validation. As we'll talk about in a little more detail, but the best choices for k, the number of folds, is usually about 5 or 10. Okay, so, and I'll explain, we'll talk about that in a few minutes about why those are good choices. But let's fix here k equals 5. So I've taken the data set, I've divided it at random, the samples, into 5 parts, again, of size about the same. If
the red box looks a bit bigger, right?
Okay, well that's my lack of drawing ability, but anyway, it's supposed to be the same. That's trying to squish the word validation in. So the boxes are supposed to be about the same size and number of observations. But in this case, the first part's the validation set, the other 4 are the training parts. So what we're going to do, what cross-validation does, it forms these 5 parts. We're going to train the model on the 4 training parts, put together as one big block, take the fitted model, and then predict on the validation part and record the error. And then that's phase 1. Phase 2, we're going to the validation set will be part 2, this block. All the other 4 parts will be the training set. We fit the model to the training set and then apply it to this validation part. And in the third stage, this is the validation piece, etc. So we have 5 stages where in each stage, one part gets to play the role of validation set. The other 4 parts are the training set. We take all the prediction errors from all 5 parts, we add them together, and that gives us what's called the cross-validation error. So now in algebra, I'll basically give you the details of what I said in words. So we'll let the k parts of the data be C1 through CK. So these are the observations that are in each of the 5 parts. Remember, k was 5 in our example. And we'll try to make the number of observations about the same in every part. Of course, if n's not a multiple of k or 5, we can't do that exactly, but we'll do it approximately. So we'll let n sub k be the number of observations in the kth part. So here's the cross-validation error rate. Basically, this is the mean square error we get by applying we fit to the k-1 parts that don't involve part number k. That gives us our fit yi hat. For observation I.
It's 4/5 of the data in this case.
Right. And then we add up the error. This is the mean square error that we obtain now on the validation part using that model. So this is for the kth part. And now we do this for all 5 parts in turn, the 5 acts of the play, and then we get the cross-validation error rate. Okay. And a special case of this is leave one out cross-validation, where the number of folds is the same as the number of observations. So that means in this picture, that actually would be 1 box per observation, and in leave one out cross-validation, each observation by itself gets to play the role of the validation set. The other n-1 are the training set. Okay. Now, actually, leave one out cross-validation there's a nice special case of that. It represents a nice special case in the sense that this cross-validation can be done without actually having to refit the model at all. So in leave one out cross-validation, at least for a least squares model or a polynomial model, if the cross-validation, leave one out cross-validation has the following form. So the yi hat is now just to fit on the full data set. Hi is the diagonal of the hat matrix. So have a look in the book for details, but the hat matrix is the projection matrix that projects y onto the column space of x to give you the fit.
This is something that can get computed easily when you fit your least squares model.
So go ahead, Trevor. Yeah.
Yeah, we don't we haven't emphasized it, but it's available. It's one of the things that's available when you fit your least squares model.
So the overall point of this is that to do a leave one out cross-validation for these particular models, you don't actually have to leave anything out. You can do the fit on the overall data set and then extract the information you need to get the cross-validation sum of squares.
And it's interesting because the HI tells you how much influence an observation has on its own fit. It's a number between 0 and 1. And so if an observation is very influential on its own fit, you can see it punishes the residual because it divides by a number that's small and it inflates the residual. So it sort of does the right thing here.
Okay, so, but a better choice, although leave one out cross-validation does have this nice computational formula, for most of the methods we talk about in this book and most statistical learning methods, it's better to choose K to be 5 or 10 rather than have leave one out cross-validation. And why is that? Well, one problem with leave one out cross-validation is that each of the training sets look very much like the other ones, right? They only differ by one observation. So when you take the average, cross-validation is you take the average of errors over the n folds. And in leave one out cross-validation, the n folds look very similar to each other because the training sets are almost the same. They're only different by one observation. So as a result, that average has a high variance because the ingredients are highly correlated. So that's the main reason why it's thought, and we agree that a better choice for K in cross-validation is 5 or 10.
On the other hand, the leave one out cross-validation is actually trying to estimate the error rate for the training sample of almost the same size as what you have. So it's got low bias, but as Rob said, high variance. So actually, picking K is also a bias variance trade-off for prediction error here. And as Rob said, K equals 5 or 10 tend to be a good choice.
So on the next slide, we've got a comparison of leave one out cross-validation and tenfold CV for the auto data. Remember, before we saw with twofold validation, with just validation into two parts, we got a lot of variability between when we changed the sample the half sample that we took. Now let's see what happens with leave one out cross-validation. We get a curve that's again got the minimum around the same place as we saw before, and then it's pretty flat after that. Tenfold cross-validation, now again it's also showing the minimum around 2, but it's there's not what we're seeing here is the tenfold cross-validation as we take different partitions into 10 parts of the data, and we see there's not much variability. They're pretty consistent. In contrast to when we divide into 2 parts, we got much more variability.
And those get averaged as well, those curves on the right.
Right, exactly. So, yeah, right. So they're averaged together, which we saw here. They're averaged together to give us the overall estimate of cross-validation, which the overall cross-validation curve will look very much like this with its minimum around 2. Okay, this is figure 5.6 from the textbook, and this is the simulated data example, which was from figure 2.9 of the book. Just recall that this is smoothing splines in 3 different situations. In this case, the true error curve is the blue curve. And again, these 3 different functions that we're examining. This is mean square error for simulated data.
The true error curve, how do we get that, Rob?
Well, it's simulated data, so we just...
so we can get a very big test set
exactly
and estimate the error exactly.
Leave one out cross-validation is the black broken line, and the orange curve is tenfold cross-validation. So we can see, what do we see? Well, here we see that test error curve is a little higher than the tenfold and leave one out cross-validation. The minimum's fairly close, but the minimum of cross-validation is around 8, whereas the true curve is minimized around 6. In this case, the 2 cross-validation methods are doing a better job of approximating the test error curve and have the minimum, well, the minimums, again, they're fairly close, not exactly on the mark. Black curve is minimized around 6, and the true error curve is minimized around maybe 3.
Although those error curves are fairly flat,
yeah.
So there's obviously a high variance in where the minimum should be.
Right,
and then it doesn't really matter where,
That's right. It's not going to matter much if you choose a model with flexibility 2 or maybe even 10 here, because the error is pretty flat in that region. And then the third example, the two cross-validation curves do quite a good job of approximating the test error curve, and the minimum's around 10 in each case. Okay. So actually I said this already, but I'll say it again, that one issue with cross-validation is that since the training set is not as big as the original training set, the essence of prediction error will be biased up a little bit because we have less data we're working with. And I also said, and I'll say again, that leave one out cross-validation has smaller bias in this sense because the training set is almost the same size as the original set. But on the other hand, it's got higher variance because the training sets that it's using are almost the same as the original set. They only differ by one observation. So k equals 5 or 10-fold is a good compromise for this bias variance trade-off. Okay, so we talked about cross-validation for a quantitative response, and we use mean square error. For classification problems, the idea is exactly the same. The only thing that changes is a measure of error. Of course, no longer use square error, but a misclassification error. Otherwise, cross-validation process is exactly the same. Divide the data up into k parts. We train on k-1 parts. We record the error on the kth part, and we add things up together to get the overall cross-validation error.
It looks like a weighted average in that formula, right? There's nk over n.
Well, do you want to explain that?
Because each of the folds might not be exactly the same size. So we actually compute a weight which is proportional to this, which is the relative size of the fold, and then use a weighted average.
Right, and if we are lucky that the n divides by k exactly, then that weight will just be 1 over k, right. One other thing to add, which is that since this cross-validation error is just an average, the standard error of that average also gives us a standard error of the cross-validation estimate. So we take the error rates from each of the folds. Their average is the cross-validation error rate. Their standard error is the standard deviation of the cross-validation estimate. So here's the formula for that. So this is a useful quantity, and when we draw CV curves, we should always put a standard error band around the curve to get an idea of the variability. So in these previous pictures, we should have had a standard error band around the curves to give us an idea of how variable they are. I say here it's a useful estimate, but not quite valid. Why is that? Dr. Hasty?
Well, I wonder why. Well, the thing is, we compute in a standard error as if these were independent observations, but they're not strictly independent. Error sub k overlaps with error sub j because they share some training samples. Right. So there's some correlation between them. But we use this anyway.
We use it, and it's actually quite a good estimate, and people have shown this mathematically. Again, the important point being that the cross-validation separates the training part of the data from the validation part. When we talk about the bootstrap method, the next part of this section, we'll see that that's not the case, and that's going to cause a problem. So cross-validation explicitly separates the training set from the validation set in order to get a good idea of test error. Okay, so this again, I want to reemphasize that cross-validation is a very important technique to understand, both for quantitative response and cross-validation and classification.